Hi, welcome back. We're up to Lecture 3, Segment 3, and this last segment of Lecture 3 is on scales of measurement. Now, in Lecture 3, I've sort of been emphasizing how important it is to know what type of variable you're dealing with, and emphasizing how important it is to look at your distributions in your variables. It's also really important to keep in mind what scale of measurement you're dealing with. So this last segment, which will be a slightly shorter segment, is just talking about different scales. We've already dealt with this in the last segment by looking at the body temperature example. So for all those histograms, I presented the histograms first in degrees Fahrenheit, then in degrees Celsius. Those are just two different scales of measurement to measure temperature, right? So I think we're all used to dealing with scales of measurement. But in statistics, what's nice is there's a standard scale, and it's called the z-scale. So any score from any scale can be converted into a z-scale with z-scores. And this allows for really efficient communication across statisticians. Scientists can share data, different researchers can share data. If everything's converted to a z-scale, it's very easy to interpret. And it's very simple calculation. How do we convert what I'll call a raw score to a z-score? It's just this formula right here. We just take the raw score, that's x, subtract the mean, m, and divide by the standard deviation. And we haven't covered summary statistics in detail yet. We'll do that in the next lecture, so you'll see exactly how to calculate mean and standard deviation if you're not familiar with that already. But that's it. It's that simple a calculation. So we'll just take the raw score, subtract the mean, divide by the standard deviation. That gives us a z-score. And if we do that for every score in a distribution, then we can put our distribution on this common metric, the z-scale. So what's also nice about a z-scale or z-scores is the mean z-score in any one sample is always going to be 0. Right? So I take the raw score, subtract the mean. If my raw score is the mean, so say body temperature, the average body temperature in Fahrenheit is 98.6. So 98.6 minus the mean, assuming a normal distribution, 98.6 minus 98.6 would be 0, divided by whatever the standard deviation is would give me 0. So the mean in any z-score distribution is going to be 0. What's nice about that is if you have a negative z-score, then I know your score is below average. And if you have a positive z-score, then I know you're above average. So again, let's look at this body temperature distribution. Here it is again in degrees Fahrenheit. It's this nice normal distribution. Here it is again in Celsius. Again, nice normal distribution. Here it is in terms of z-scores. Again, we did this in R, and R sort of did the breaks a little bit differently for this graph, but it's still a nice normal distribution. And most importantly, the average is 0. So the average body temperature in terms of z-scores is 0. These are the same exact numbers from histogram to histogram to histogram. It's just in degrees Fahrenheit, degrees Celsius, or in z-scores. It's the same exact numbers. We just converted them. Direct conversion. So just to be clear, let's assume we have a normal distribution of healthy individuals where the mean body temperature is 98.6 degrees Fahrenheit and the standard deviation is about 0.5 degree, so 0.5. Suppose I pick one individual from that distribution at random, and that individual's body temperature is 99.6 degrees. Now I want to convert that raw score, that x 99.6, to a z-score. Well, all I have to do is apply this z formula. I take the raw score, 99.6, subtract out the mean, 98.6, divide by the standard deviation, which was 0.5. So that's just 1 over 0.5, or 2. So this individual's z-score is positive 2. There are 2 standard deviations above the mean. The other thing we can do once we convert everything to z-scores and look at histograms in a z distribution is we can easily get percentile rank, which is a useful statistic to get when we're looking at descriptive statistics and where individuals fall relative to others within a distribution. So the percentile rank is just the percentage of scores that fall at or below that score in a distribution. So if we're dealing with a perfectly normal distribution and we've converted everything to z-scores, then I know that the percentile rank for a z of 0 is 50%. Right? If I have a nice normal distribution, I've converted it to z, so the mean is 0, then below that score is going to be 50% of the distribution. In other words, the percentile rank of a z of 0, or 98.6 degrees Fahrenheit, is 50%. 50% of the distribution falls below the mean. So to sum up, the z-scale is the standard scale that we use in statistics. It's very efficient. It's very nice for communication. I can take any raw score, convert it to a z-score, and once I have a z-score, I can get a percentile rank. So these conversions are very common in statistics, and at this point, you should be comfortable doing those types of conversions. And we'll do those in lab and perhaps on the next homework. And that's the end of this segment.